In this video, we explain power factor and reactive power in a way that you have never heard or seen it before. So if you're involved in the solar industry or you're just an electrical contractor and you want to know how power factor and reactive power is busy changing the power dynamics in your installation, then this is a great video to watch. My name is Karel Balak. I work for a company called PQRS. I've been presenting electrical and engineering related training for the last 15 years, and you are definitely going to be enjoying this video. Okay, so the red line is the zero line, and we've got this alternating waveform above and below the zero line. There are two axes over here. We've got an axis over here that gives us the voltage. So this is the voltage. And if we look at that over there, we'll see that the blue line represents the volts. Then we've got the red line. The red line works on this axis over here. And the red line gives us the amps. When we look at power is equal to volts times amps. As soon as you have reactive power in your network, it distorts your sine wave. If I change the power factor up here to 10 degrees, it changes the waveform. So I'm going to just undo that quickly. I want you to have a look at what's happening over here. So at the moment, that's unity. The minute I change the angle, the phase angle we've got there is basically the difference between the current and the voltage. So if we change the phase angle there, it changes the wave and the shape of the wave. So we can, if we look at this, we can see we've got a 5 kilowatt load at 230 volts. Now, power is equal to volts times amps. Current is equal to power over voltage. So that is 5,000 divided by 230 volts, 21 amps. So what we see up here is, so the volts is blue. So we've got the voltage of 230 volts sitting there, and we've got the amps sitting over there. Now, what I want you to have a look at that is interesting is, so kilowatts is equal to volts times amps. We've got in our table, we've got volts there, and we've got amps sitting over there. Now, what I found interesting, what I want to show you guys is this. What this site has is, it's a 50 kilowatt Daya inverter. What it's showing us is it is drawing 3.8 kilowatts. So it's drawing 3.8 kilowatts, but if we measure the amount of amps that runs through the inverter, what we see is 55 amps. If we take 55 amps and we multiply that, so I'm going to, what was the question? Is it drawing or supplying? Jeffrey, it was supplying. So the inverter, the load was, so it depends on how you look at it. The load was drawing and the inverter was supplying. I'm sorry. I didn't do that intentionally. You wanted to know. So the load was drawing the power and the inverter was supplying the power. Let me show you again. So you should be able to see that. So that is out to the load, and the test is measuring 55 amps. But if you look at the screen over here, there's your load sign. It's only drawing 0.16 kilowatts from Eskom. It's getting about 1.7 if I'm reading it right. It's a bit blurry, but let's assume it's 1.7 kilowatts from solar and 2.6 kilowatts from the battery. We can see those little arrows over there. So the PV is supplying, the batteries are supplying, Eskom is supplying, and the load is demanding 3.85 or 3.86 kilowatts. So our load is 3.8 kilowatts. But our tester is measuring 55 amps. Now, if we take 55 amps and we multiply it by the voltage, so amps multiplied by voltage multiplied by the square root of 3 because it's three-phase power, and we divide that by 1,000, 55 times 400 times 1.73 divided by 123. 38. So the answer we've got there is 38. What we've measured was 38 kVA. So the load was only 3.8 kilowatts. But the amount of strain on the inverter was the equivalent of 38 kVA. Do you guys see what we've just calculated? That means that this over here has to be out of the ballpark. So what I wanted to do was I was trying to find a way to express what I've just calculated there visually. So we've got a 3.8, you can make that 400 volts, and the table adjusts. We can make the power in kilowatt 3.8. So what it's supposed to be drawing, there we go. What it's supposed to be drawing is 3.8 kVA. But that's when the power factor is at unity. So if we mess around with the phase angle over here, which is exactly what I want to do. So let's say the phase angle is 30 degrees. It turns into a lagging power factor. Our power factor is now 0.87, but our amps is 11 amps. We change that to 60 degrees. Our power factor is now 0.5. And the current in amps is 19. If we take it back to 30, the current is 11. Do you guys see where the amps are going? If we take this up to 70 degrees, it makes our power factor 0.34. It's taken our amps up to 28. If we make the power factor even worse, that steps it up to 91. It wasn't that bad. So let's make it 75. The amps we measured were 55. So that would have been there. So the power factor at that facility was 0.17. Look at what's happening to the amps. 55 amps on a 3.8 kilowatt load. So the power factor is bad, but the power factor is bad, but it doesn't add to the kilowatt hours. Yes, that got me thinking. Oh my word, I couldn't, and it doesn't matter what you search, there are no answers. Everybody on the internet tries to explain the kilowatt or the kVA beer analogy, or they want to explain how it works, but nobody could explain, not in the videos that I looked at, could explain why it's not billed in kilowatt hours. So what I did was I went one step further. I said, okay, I want to calculate if my phase angle is 0. I want to calculate how much energy is being consumed. So I've got this whole table on the left-hand side where we've actually calculated the amount of energy in each fraction. There, if I click on the graph there, we calculated the energy in each one of those fractions, and then we added it to give us this graph over here. So the graph on the right-hand side shows us the amount of energy that is drawn, in other words, kilowatt hours, that is drawn when we run a load at this particular power factor under these particular conditions. So what I want to do is I'm just going to change this back into single phase because it's just easier. I'm going to change that back to 5. So now we've got a 5 kilowatt load at single phase, because for me single phase is just easier because we just have one sine wave to worry about. So whatever is contained in, I'm sure you guys can see my cursor, but I'll be a bit more specific. Whatever is contained in that portion, and in that portion, that is what we are built for. What this graph shows us, so we've looked at the graph on the left. What the graph on the right-hand side shows us is, first of all, it shows us the amount of power that we're drawing there. But obviously, power is instantaneous. So this whole triangle over here would represent power over time. So that gives us kilowatt hours. Essentially, it actually reflects watt seconds, but we can view it as kilowatt hours. So everything above the line, everything above the red line over here Yo, guys, if you understand what I'm saying and you're kind of keeping up with what I'm saying, that is going to be epic. So everything above the line at the moment is being used for work because our power factor is at unity. Our power factor is at 1. So all of the power that we are drawing is being used for work. Now, as soon as we start messing around with the power factor, so let's change the phase angle. I want to get back to this triangle quickly. So when we change the phase angle, what I'm changing is I'm changing that angle over there. So what it's busy doing is it's pushing this angle up. And as it's pushing that angle up, it's actually making this leg, this kVA leg longer, which means that it's actually in reality also making the kVAr or the reactive power leg longer. So what we are changing when we're changing the phase angles, we're changing that angle, and that changes your kVA as well as your kVAr. If I change the phase angle to, let's just change it, I'm going to change it dramatically. So I'm going to change it to 60 degrees. What is evident is the angle between, or the massive gap, here between the current and the voltage. And what is also evident now is that previously we just had a line above the red line, but now we have below the red line in this. So at the moment, I'm looking at this graph over here. So maybe what we should be doing, let me take that away and that away and that away. So that's the graph I'm looking at the moment. The green block says this is power that is being used for work, is everything above the red line. Everything below the red line is power that is being used, but it's not being used for useful work. So our power factor has degraded to 0.5 at a 60-degree angle. It's 0.5, and this is what we are being billed for. Yeah, I don't know, this is like hyper exciting. This is what we are being billed for. Now, have a look at what I did was there are a couple of things we want to have a look at over here. Okay. Wait. So was when the power factor goes out of whack, the current that we are drawing is going to go up. So if this represents, so if I want to be smart, now, I'm going to stick to the same color coding. Where red represents current. If the current is 55 amps, this current value has grown. So we are drawing more amps. But what is busy happening is in the simulation, it's pushing some of the power that's being consumed below the line. Look, that becomes a negative, but the amount of energy that we're consuming over here stays the same. Now look at what happens when I change So I'm going to change the power factor. Look at the energy that's being consumed and look at the current in amps, and then look at this graph over here. So I'm going to change the phase angle back to, let's change it to 30 degrees. Our power factor has improved. If you have enjoyed the information and you've enjoyed how it's been presented, why don't you consider like and subscribe to this channel to get some additional free content, or alternatively join one of our courses. And there's a lot more information where this information came from. Thanks for watching. Cheers.